All right, we're ready to begin the second part of lesson 21, which is another formulation, and this is the Mystic Coffee Shop that you'll find on page 649 of your textbook. And I'm going to read again a little bit about the Mystic Coffee problem. You can follow along, but we're going to go through the same process. What's the decision? What are the decision variables? And how do we formulate all the constraints? So first of all, here's the problem. The Mystic Coffee Shop blends coffee on the premises for its customers. It sells 3 blends in 1-pound bags: Special, Mountain Dark, and Mill Regular. And we'll call those Special, Dark, and Regular. It uses 4 different types of coffee to produce the blends. It uses Brazilian, mocha, Colombian, and mild coffees to go into the blend. The shop used the following blend recipe requirements. I'm going to come back and talk about those later. Then it goes through and describes how much it costs for each of the 4 coffees. Brazilian is $2 a pound, mocha $2.75, Colombian $2.90, and mild is $1.70 per pound. And what it says, it sells the Special for $6.50 a pound, the Dark for $5.25 a pound, and the regular blend for $3.75 a pound. And then it says the shop has 110 pounds of Brazilian, 70 of mocha, 80 of Colombian, and 150 pounds of mild coffee each week. And the shop wants to maximize profit. So how do we formulate and solve this problem? And I've set up a table here. And the reason I use the table is to just give you an idea that it has exactly the same basic structure as our transportation problem, but it's called a blending problem. And the reason it's a blending problem has to do with the blending constraints that we'll look at here in a few slides. So let's see why this has the same structure. So first of all, here's just another visual representation of the problem. We have 4 different coffees, as we've talked about: the Brazilian, mocha, Colombian, and mild coffee. These are, if you will, these are our raw materials. And then we are taking these and putting them into 3 different blends of coffee: the Special coffee, the Dark coffee, and the regular coffee. And so the question then really becomes, how do we we're going to put Brazilian into Special, we're going to put this Brazilian coffee into Dark blend, we're going to put it into our regular blend. We may choose to put mocha into Special, regular, Dark or regular. And then, as you might expect, we're going to do the same for the Colombian. Can go into any of these blends. We can have mild go into the Special, into the Dark, or into the regular. And so hopefully you can see that it has exactly the same structure, except now we've got four coffees as our raw materials or our supply, and that we have 3 blends here as our demand. So as we saw in our previous in the seaboard trucking problem, each one of these arrows in this diagram will represent a decision variable. So hopefully right away you can see how many decision variables do we have. If nothing else, you should be, if you can't even define it right now, you can see we have 12 decision variables. There's 3 options for the mild, 3 for the Colombian, 3 for the mocha, 3 for the Brazilian. So there's 12 different 12, and I'm going to abbreviate 12 decision variables. So then the question is going to become, and again, we're going to use this structure to help us construct our constraints. And we'll see how that works in a few slides. All right. So now we're going to talk a little bit more about the decision variables. The first thing, I'm going to try to draw this again. I should have brought this over, but here, first of all, we've got a coffee. Here's the Brazilian coffee, and we've got our 3 blends. So, this is the special. This is the dark. This is the mild, and this is our Brazilian coffee. And if we just look at this one situation with our Brazilian coffee, there's 3 options. We can put Brazilian coffee into the special blend. We can put Brazilian coffee into the dark blend, or we can put Brazilian coffee into the mild blend. So given these variable representations, BS, BD, and BM, what do they each mean specifically? Well, BS is going to be the same as the amount. I'm going to change that. I'm going to say the number of pounds of Brazilian coffee put into a special blend. And as you might consider, D is the number of pounds of Brazilian coffee into the dark. And lastly, BM is the number of pounds of Brazilian into the dark, into the mild. All right, so you can repeat this. You can repeat this 12 times, or you can use a shorthand notation, because you would have 3 for 3 for the mocha, 3 for the Colombian, 3 for the each. You could write this out 12 times, or a simpler, quicker way to do this, once you see the pattern, is we're going to say that variable I, J, is going to be the number of pounds of coffee I put into blend J, where I equals, and we're going to use Brazilian, O for mocha, and again, you can use any term you want. We're going to use C for Colombian, and it's not mild. I've made them, and mild. Mild is a coffee, not this. This is not. This should be. Let me make this correction. This should be not mild. I made a mistake here. This should be regular coffee, not mild. And this should be not BM. This should be be R is the number regular blend, not mild. There's not a mild blend, it's a regular blend. My apologies. All right. But the principle is the same. So AJ is the number of pounds of coffee of type I put into blend J, where I is either Brazilian, mocha, Colombian, or mild, and then where J is either the special, dark, or the regular blend. And so that will, in one quick sentence, will give the definition for all of your decision variables. Okay. So now let's continue. Again, if that, think through that carefully, make sure you understand. And again, there's going to end up to be 12 decision variables in this problem. Please make sure you think about that carefully. All right, now let's look forward. This is at the objective function. And this is going to be a little bit different. And so I'm not going to go through every one of these, but I'll go through a couple of these to show you how this works. So let's think about the Brazilian coffee that's going to be placed into the special blend. Okay. So the Brazilian coffee is going to be our goal, our objective is to maximize our profit. So if we put a pound of coffee, and again, remember, we're not just making 1 pound, we're making hundreds of pounds of this coffee. But if we put a pound of Brazilian into this coffee, that's going to cost $2, and we're going to sell that for $6.50. So the net profit for Brazilian coffee put into the special blend is going to be equal to that $6.50 minus $2. And of course, that arithmetic is easy. That's $4.50. So if I can type $4.50. So $4.50 is the net profit. And again, this would be the term that you would use in the objective function. And so your objective function term is going to be 450 times Brazilian into the special blend. Okay, and we're going to do this calculation 12 for each one of these 12 alternatives. Let's just take a look at another one, just for hypothetically. And this is arithmetic is again going to be easy for the mocha that goes into the regular. All right, what's going to be the net profit? Well, the net profit is going to be the $3.75, 75 minus, it's the profit minus the cost of the mocha, which is $2.75. So the net profit is, again, in this case, $1. And then the term that's in the objective function is going to be $1 times mocha O that goes into $1 times O that goes into and that's the term that goes into the objective function. Let's take a look at another one. Let's take a look at another one. Mild that goes into the mild that goes into dark. What's the net profit? Net profit is $5.25 minus $1.70. So the net profit, this is a little bit, let's see if I can do this. It's going to be $3.55, I believe. Let's do the arithmetic. Yes, $3.55. And so the term that's going to be associated with this is going to be again $3.55 times mild that goes into the dark. Okay. So again, you'll do this 12 times. You'll come up with 12 different terms that goes into your objective function, one for each one of the possible combinations of price and cost. All right, now we're going to look at some constraints. And the first one are the supply constraints. And again, this is exactly what we've had previously with our supply constraints, with the seaboard trucking problem, because we're going to start out and we have 110 pounds of Brazilian. And so our limit is 110 pounds. And that Brazilian can go in either to the special or the dark or the regular. And so our supply constraint for the Brazilian, as you might imagine, is going to be that Brazilian that goes in, the total amount is the Brazilian that goes into the supply, special, plus Brazilian that goes into the dark, plus the Brazilian that goes into the regular. And that's going to be less than or equal to 100 pounds. And as you might expect, you'll have those constraints, similar constraints for the mocha, for the Colombian, and the mild. And again, just looking at the Colombian, this is going to be CS plus CD plus CR, and that's going to be less than or equal to that supply of Colombian, which is 80 pounds. So hopefully you can see that each one of these is going to be added together, plus, all of those are added together. The three terms are added together, and it's going to be less than or equal to 70 pounds. And these three will be added together. And those three added together will be less than or equal to 150 pounds. And so again, there's going to be four constraints. 1, 2, 3, 4 constraints for each one of those supplies. All right. Now we get to the, we had the one twist with the objective function. Now we get to the one twist that's that makes this problem unique. And this is the blending problem. Now, I'm going to read through that table, and I'm going to talk through one example and then leave it to you to convince yourself and to make sure that you understand and can compute the other constraints that are associated with this. So in the table of the problem statement, it says the shop uses the following blend requirements. So for the special blend, it must be at least 40% Colombian and at least 30% mocha. Now, the first thing about those is those are two separate constraints. And you might ask yourself, well, where do these requirements come from? Well, they're blending requirements. They're somewhere in the Mystic Coffee Shop. They've had a taster and maybe even a chemist or a coffee specialist say, in order to achieve the taste that we achieve, this is how it should be blended. And so the first one we're going to look at is the requirement that the special blend must have at least 40% of the Colombian coffee. Okay, so excuse me. In our graphic representation, we know that the special blend can have either Brazilian, mocha, Colombian, or mild coffee that's put into there. So the question is, you might ask yourself, well, how do I deal with this? How do I know what 40% is? How do I calculate that? And the best way, or one of the ways that I can try to get you perhaps to understand this is as follows. Let's suppose, rather than using the decision variable names, let's actually put numbers on this. And let's suppose, just to make things easy, that it turns out that we put 10 pounds of Brazilian in, and we put 20 pounds of mocha in, and we put 30 pounds of Colombian coffee in, and we put 40 pounds of mild coffee in. All right, and so now we know that all of these together, the 10, 20, 30, and 40, we've got 100 pounds of our, 100 pounds of our special blend. Hopefully you 10 plus 20 is 30, plus another 30 is 60, plus 40 is 100 of special blend. All right. So if we wanted now to compute the amount of special blend, the amount of Colombian that's in special blend, how would you compute that? Well, what we know is we've got 30 pounds of the Colombian in this total amount of special. And so this is not higher level math, but we've got 30 pounds of Colombian into the special, and there's a total of 100 pounds, and so that's 30%. And so in this case, you'd see we would not satisfy, that's not satisfies the 40%. Okay. So now how do we convert this and make sure that we can meet this requirement? The first thing that we're going to do, I want you to notice, is that we've got 30 pounds, all right, of Colombian that's in our special, and we've got 100 pounds in total into this special. And this is going to seem trivial, but I hope it helps. That's going to be 10. We know we're going to have 10 pounds of the Brazilian plus 20 pounds of the mocha plus the 30 pounds of the Colombian plus the 40 pounds of mild. And what we want to have, it doesn't, we know, but we want to have this to be at least 40%. See if I can go slowly and get this. That has to be at least 40%. Everyone agree with that? All right, so now the way to do this, and hopefully this will help make a little bit more sense. All right, we've just taken these numbers, these hypothetical numbers, and we've created this ratio. And now what I want you to do is to think about how is working this backwards, because first we started with our decision variable definitions, and then we went from those into our numbers. So what I want us to do now is now take these numbers and go, if you will, backwards, and use instead of using the numbers, use our variable name. Remember, what's a variable? It's just a letter or a symbol that stands for a number. And so I'm going to try to do this. What we want to do is we want to take this ratio. We're going to create another ratio, but this is going to be in terms of our decision variables. And in order to do this, I'm going to take this 30. What's this 30? Well, this 30 was the representation of the Colombian that's in the special. And so our new ratio is going to be, the numerator is going to be the Colombian that's in the special. Okay, so what's then the denominator? Well, what was the 10 a surrogate for? It was a surrogate for the Brazilian that's in the special. The 20 is a surrogate. The 20 is a surrogate for the mocha that's in the special. The 30 again is a surrogate, is a representation of the Colombian in the special, and of course the 40 for the mild in the special. So what I'm going to do, the denominator then, in terms of our decision variables, is the Brazilian that's in the special plus the mocha that's in the special plus the Colombian that's in the special plus the mild that's in the special. All right, and so there's our ratio. And of course, we know now that we want this to be, we want this ratio to be greater than or equal to, greater than or equal to our 40%. All right, so the problem is, we've got a little problem. The problem is now, unfortunately, this term, this ratio, is not a linear term, but we can convert this because it's a ratio of two of the same variables. What we need to do is convert this into a linear term by doing a little algebra. Now, I'm going to pause here for a second. I want you to think about this and make sure that you understand this, because we've got 6 of these different constraints to model. We've got at least 30% of the special needs to be mocha. At least for the dark, it has to be at least 60% Brazilian, but it has to be less than 10% mild. And for the regular, it has to be less than 60% mild, but at least, and also at least 30% Brazilian. So there's 6 of these different blending constraints that we have to address. But if you get the relationship for each one of these, then you can, for just this one, then you can easily go through and model, convert the other requirements into those 6 constraints. So let's look one step forward. All right, and to answer the question about how do we do this, well, first of all, here's our relationship that we just talked about. This is that ratio. All right. And then we're going to do just a little algebra. We're going to first cross multiply by this denominator. So that takes the denominator out of the left side and moves it over to the right-hand side, multiply that by 0.4. We distribute the 0.4, and then I'm going to subtract the next step. I'm going to subtract CS from both sides. Now, you should remember, of course, that's 1 CS, 1.0 CS. So now once I take minus CS, then the left side goes to 0. These terms stay the same, but 0.4 minus 1 is negative 0.6 CS. And then, of course, that term is the same. And this is the same is just flipping those around. You can multiply through by negative, and if you multiply through by a negative, it changes the sign to greater than or equal to. So there's many different forms for this, but what you should end up with is something that looks similar to this for your constraint. All right, and again, this is just one of the 6 constraints. So now I'm going to go to the full formulation. Okay, this is the full formulation for the Mystic Coffee problem. Here's the definition of our decision variables, our maximized profit. You'll find in here each one of the terms we talked about. There's the dollar for the mocha into the regular. There's the, where was it? $3.25. Maybe it was $3.55 for the mild into the dark. $4.50. Here's the representation of all of our blending constraints. This was the first one that we worked. These other 5 would challenge you and encourage you to work through all of those other 5. Once you understand that, it's not very difficult to do. And then, of course, here's our supply constraints. And then again, we don't want to forget non-negativity. I'm not sure why this is a problem down here, but the way that should read, just to be complete, is it should be IJ is greater than or equal to 0 for all combinations of I and J. And again, those combinations refer to the combinations of I and J that you defined up above. Okay, so hopefully that makes sense. There were 2 steps in this that were confusing a little bit, that new, the blend percentages. So work through these, and convince yourself that this objective function is correct. All right. So hopefully, again, as always, if you have questions, don't hesitate to contact me.